So last lecture we have discussed B physics. And B physics, again, what I'm saying, that there is no K physics, there is no D physics, but there is a B physics. And as I said also, the hope is that new physics, if it exists at high scale, may show up first in this B physics, in the physics of heavy quarks. So this is why it's of great interest. So far, we are not yet found really establish something beyond the standard model. And at the same time, in the last few years, how we are saying paradigm has changed, and now people are looking for physics at very light scales. So maybe something exists much lighter than electron or neutrino. So a very active area is related to axions or axion-like particles, which actually related to CP violation, what we have discussed. Let me add a little bit more on B physics, just to show you variety and richness of this area. Actually, this is a very important area of research of these days. So maybe some of you will work on this. We have already discussed how, using B physics, we have fixed parameters of CKM matrix. Few more things. Oscillations of neutral B mesons. B0 bar. I have mentioned already this phenomenon in connection to neutrinos. When in vacuum, without any external forces and influence, one neutrino species can be transformed into another. In the same way, B mesons, B0, can be transformed into B0 bar. This phenomenon actually has been observed already for K0 bar system. So let me remind that B0 is the system of two quarks, B bar and D. B0 bar is B, D bar, it's conjugate. And what is important that these states have definite flavor. So clearly this has B number -1 and isospin. And this has B number, this is -1, this is +1, and isospin, which is instead of -1 over 2, this 1 + 2. So these are the states with definite flavor. It turns out that they do not coincide with mass eigenstates. So they have no definite masses, but mixtures of two other states with definite masses. And therefore, there are oscillations or spontaneous transition of B0 to B0 bar, this way. The time of this transition, of the length, so if you produce B0 and let it to propagate, gives you the mass difference of mass eigenstates. And delta M has been determined, and it is something like 3⁻⁴ electron volts. Extremely small. Remember, the masses of this B is around 5 GeVs. And the mass speed is extremely small. Of course, this is related to the fact that still there are some interactions which actually lead to mixing and lead to some split of the mass eigenstates. What is interesting about this system, in contrast to neutrinos, is that these B and B0 bar are also decaying particles, and it turned out that delta M, the mass difference, over decay rate for this system is something like 0.72. So, which means that you have interesting effects related to interplay of decay and transition of B0 to B0 bar. Another interesting thing, in B system, they also have so-called flavor-changing neutral currents. In particular, B0, S. So this is the state which contains S quark instead of D quark here. Can decay, apart from many other channels, into mu plus and mu minus. This is an analogy of what we had for K0, where we have also flavor changing neutral currents. Branching ratio, well, let me write probably the plot. So that's what happens here is we have BS bar, which is transformed into mu plus, mu minus. And there is something here which actually leads to this transition. So here we deal to the flavor changing neutral current B and S have the same electric charge, -1. And so we have transition of B somehow to S. So we have changed the flavor, B go to S. And this is neutral current which is responsible for such a transition, or neutral interaction somehow. So we have here transition of B to S. Now, the branching ratio of the decay, that is the fraction of total decays onto this mode, is 2.7 plus minus plus 0.6 minus 0.5 10 to the minus 9. That's approximately the same as we had for K0 decay into mu plus mu minus. And this transition again occurs because B can go through U, charm quark, right? So that's S, and this way. So that's because of this transition, similar to what we had for K0. Here is mu. And here are U. It can be also charm. And since now we have introduced the third generation of quarks, you also need to take into account top quark. And in fact, top quark, we will see it has very large mass. And so gene mechanism essentially doesn't work for this. So we have big mass difference. Still kind of gene mechanism acts, of course. And that explains the appearance in the loop of this transition, explains smallness. Well, let me put here S bar, and here is B. There is interesting decay mode which is used also to measure CP violation. We will discuss discovery of CP violation, and that has been discovered in K mesons system, but also B decays show up CP violation. And one interesting channel, and I will give you the exercise to find diagram for this transition, decay into J psi plus K0S. So this is interesting channel which was used to see CP violation effects. So what we have now, we actually introduced B quark to explain CP violation, is that we are able now measure CP phase, this unique phase which appears in CPA matrix, in different places. In K0s, in D, in B, in some other places. And what is interesting that CP phase extracted from these different measurements is the same. So actually this shows the correctness of Kobayashi-Maskal mechanism. The hope is always that maybe in some other measurements we will find some other effect of CP violation, which doesn't matches just a single CP phase in CKM matrix. for time being, that hasn't been found. So this CKM mechanism, it seems, works very well. Finally, you see, the area is active also when you have many experiments. If you just do theoretical speculations, that doesn't go far, you know. People are doing something, elaborate formalism, and then so on. You need to check this, or you need to actually have some connection to experiment. And fortunately, in this area, there are a number of experiments, and in the, say, last 10 years, now still they are continuing these studies. There are experiments with so-called B factories, even so. People invented this term to have B factories, machines which produce many B mesons, and so you can make detailed studies of the system. So let me say a few words on these B factories, and you will have some exercise. So what is a B factory? These are E plus and minus machines. And so what happens, you turn the energies of E plus, E minus in such a way that you produce epsilon 4s, or this is the same as epsilon prime, prime, prime. This is the heaviest. Remember we had, when we discussed discovery, we discussed that actually there are 4 states of epsilon. Epsilon 1s, 2s, 3s, 4s. And so they have different masses. And it is this, the heaviest one, which has very fast decay rate. And this is because the mass of epsilon 4s is bigger than 2 masses of B mesons. It can decay into B and B bar. And this is dominant mode of this decay. So, being precisely in resonance, so which means it match the energies of E plus and minus in such a way that square root of S is the mass of epsilon 4s. And then you have a very clean machine which produces for you B bar pairs. There are 2 these factories, bar at slack, and they use also linear accelerator and storage ring at slack. They use it. And Bella in Japan. Now there is a Bella 2 at Keck complex. And what is interesting, they are using so-called asymmetric beams of electrons and positrons. Electrons, this is for bar with energy 9 GeVs, collide with positrons, which have energy 3.1 GeVs, and this is for bar. So why they are doing this? If you would have the same energies of electron and positron, then epsilon would be produced at rest. So with equal energies of electron and positron, your laboratory frame coincides with centrum of mass frame, and therefore you would produce epsilon at rest. Just from practical point of view, it would be nice if you shift your epsilon from the production point. And so this is why they use asymmetric energies, and therefore epsilon produced in such a way will move, right? So because of unequal energies. And so it moves and then decays into BE bar. Also, Bell used asymmetric beams, and we will have exercise to actually will establish what is the energy for delta. Now this is very luminous machines, in spite of the fact that you have quite complicated stuff. You have a plus and minus which annihilates in this epsilon. The luminosities are quite big. 7.4 10 to the 33 centimeters minus 2 second minus 1. And actually, the number of B bars are several billions. So it's not a joke. Also, we have these heavy mesons and produce them in quite sophisticated way. So actually, several, I don't remember now, things are changing because they have continued to work. At least Bella 2 is working. 10 to the 9 B bar. And therefore, of course, you can do very precise measurements with this machine. Now let me make, I don't want to really to discuss this in detail. Oh, just another one. Sorry, I have forgotten to say a few words about LHC-B. At LHC, they have also detector specifically created to study B physics. This is not collider, but they have fixed target. So of course you have acceleration of protons, the same as for the main experiments when you collide protons and protons. Here you have fixed target with a number of detectors, collide proton, and then produce many secondaries. And among the secondaries you have B and B bar production. In this case, this B bar production goes through gluons. So you have collisions of quarks, and then through gluons, particles which mediate strong interactions, you produce B and B bar quarks. And these quarks actually pick up some usual quarks and form B and B bar mesons. So the goals of this experiment, spectroscopy, measurements of CP violation, checks of so-called unitarity triangle, unitarity, because all this scheme with 3 quarks of 3 generations is based on CP violation, is unitarity, and people are looking for deviations from unitarity, which may indicate actually presence of some new particles, for instance. And finally, I think already 5 years ago, some anomalies still have been found, which we call B anomalies. B anomalies. Something which doesn't match the standard model predictions. Well, if you want, I can discuss this during tutorial, but not now. And actually, my former diploma student, he was here, I think, 6 years ago or so. He did diploma thesis with me on neutrino physics. But then he did his PhD on B physics, precisely. And he has written one of well-known papers, actually, on explanation of these anomalies. So now he's a postdoc at Zurich. See, maybe some of you will work also on B physics. Again, because there are experiments, there is LHC-B, there is Bella 2, and they will produce some more data. And who knows, maybe we will discover in physics precisely, studying B mesons or particles containing beauty. Questions?
You mentioned just a few minutes. They are looking for deviation from unitarity, and that's mainly because new particles, which kind of particles?
Oh, we don't know, right? So some new quarks, for instance.
But how come, those new particles may?
Well, you see, remember, we had generations of quarks. U and here is combination of D, S, and bottom. And the same is charm, and then also W is top, And here there are orthogonal combinations of these states. It is this orthogonality, actually, that is one of the expressions of unitarity. Okay? That follows from unitarity of the matrix, because these guys are mixed the combinations are mixed, say D, CKM, S, CKM, B, CKM, and so these are combinations which are here. They are given by unitarity matrix, and then D, S, and B. So this is the essence of mixing. And we are checking unitarity of this matrix. Imagine that you have these orthogonal combinations plus some epsilon B prime. Some new quark which may be quite heavy, it might be, say, 200 GeVs or even heavier, 1 TeV, so that you do not see them immediately produced in decay. However, they enter here, and if you have this addition, then the states will not be orthogonal. And so this is the way to see some deviation from this orthogonality, check unitarity. Okay. Now we switch a little bit topic. We will probably discuss a little bit discovery of top quark, which actually happened much later. And there is a long story of discovery of top quark, but this is really already after establishing of the standard model, and probably you will discuss this in details in the second part in the next semester. What I want to discuss now is existence of quarks as real objects. Which is a related topic to the structure. Of hadrons. And I will discuss partons. So we introduced quarks. And still it is not clear if this is something which is convenient for classification of particles. That at least works. Are they real objects sitting somewhere in hadrons? What they are doing, so what are the properties of quarks inside the nucleons or hadrons? So this is the question. So tell me, who knows how it was established that quarks are really physical objects which are sitting inside the hadrons? Who tell me? How do we know that really proton is made of the quarks? And this is something which is not sitting inside. How have we established this? Okay. So let me start with Rutherford. What Rutherford has established that nuclei and proton, which is nuclei of hydrogen, have radius 10 to the minus 13 centimeters. Okay. So the question is, you have proton of this size, how electric charge, and we know proton has electric charge, is distributed inside the proton. If it is just continuous medium, or it is made of some small constituents, point-like objects inside. Remember, this is the same question Rutherford himself resolved, right? Because Rutherford dealt with what? With atom and its structure with small size nuclei and electrons around. So the question is how the proton or neutron look like, if they are like this or like that. How do we probe the structure? To probe or to see structure, we need to have microscope, right, as usual. We have microscope with good resolution, which means that we need to have lambda particles with de Broglie weight, which is much smaller than the radius of nuclei. Right? So we need to have some particles which have de Broglie weight which is smaller than the size of the nuclei. Then we can probe what is here or here. Because if you would have something like this, very big de Broglie weight, then you will not be able to distinguish these two structures. You see, the story is, and what's interesting, that the same kind of law, the same type of principles, they are emerging from in different phenomena in different areas. Well, someone has very extreme point of view that all the physics is actually harmonic oscillator. So once you know what is harmonic oscillator, then you know the physics. Well, actually here also, no need to know too many things, but just to understand that you have a repetition of the same properties in different systems. So we need to have particles with high enough energy, because lambda of P, momentum of particle, is 1 over lambda. I omit here 2 pi. And this should be bigger than 1 over the radius of nuclei. So I just inverted this relation, and this means that I need to have particle with momentum which is bigger than inverse radius of the nuclei. And this is, as you remember, 0.1 GeV, inverse of 10 to the minus 13 centimeters. So which means to probe structure of nucleon, we need to have particles, radiation, with momentum bigger than, say, GeV. In this case, we can actually probe the structure. So literally we repeat the same as Rutherford did. We need to take particles and scatter them on nucleons, and the energies of the particles should be bigger than 1 GeV, 7 GeVs. Because the bigger the energy, the smaller structures you can probe. What people use to discover structure, they used electron-nucleon scattering. Not only this, also muon nucleon scattering and also neutrino nucleon scattering. Actually, by these scatterings you are probing different things. So scattering of electron on nucleon or muon probe electric charge distribution. Right? Neutrino has no electric charge. Neutrino scattering probes weak charge distribution in the nucleon. So we deal with the process when electron scatters due to electromagnetic interactions on proton, and you have some the secondary particles X and J. So in the same way as Rutherford used scattering of alpha particles to probe structure of atom, here we use electron beam, scattering of electrons to probe structure of proton. So let me introduce here K momenta, K prime, and we have transfer momentum, which is K minus K prime. And this is nothing but 4 momentum of gamma. So it's photon, and here we have energy momentum conservation, and so you have here momentum, 4 momentum of gamma, which is K minus K prime. A scattering angle is given by the following relation. So we have K momentum is Q multiplied by sine theta scattering. So that's this angle. The first important discovery was observation of so-called deep and elastic scattering. So let me say that we call elastic scattering when electron scatters on proton, and in final state we again have electron and proton. So nothing new is produced. This is elastic scattering. Now you may, with increase of energy, have the process when you have electron, proton, and in final state pion, neutron, and again electron. So single pion production. Usually this is related to some production of resonances. Here is delta resonance, which then became to proton and neutron. So for this, of course, you need to have higher energy than here. Here no need to have any, so there is no threshold here. So this is resonance. And with further increase of the energy, what has been observed is observed the process electron, proton, and final state electron and X, which is the system of many hadrons. Nucleons and pions of K mesons. This means that you need to produce these new particles. And this means that electron should transform to hadronic system a lot of energy to produce these particles. So, this process, which we call deep and elastic, is characterized by a large Q square, large momentum transfer, right, to produce here many particles. You need to have large Q. Actually, you can consider just this part of the process. And what you have here is collision of gamma with proton and production of secondary hadrons. And of course, to produce many hadrons, you need to have high Q square, high Q. Right? Then you will have production of many hadrons in final state. So this is what we call deep and elastic scattering. It's abbreviation DIS. What is important? Not only that you have events of this type, but what is important that these events have rather high probability. Of course, due to quantum theory, because we have quantum theory, they are in quantum system, you have still some chance to produce many hadrons in final state. This is one story. But here it's often process. It's not like you have 1 out of 10 to the 9 events. Here, if you have high net energies, this process even dominates its main channel of transition, of scattering. From this relation between Q and K, and we can get that sine theta equals K over Q. And if Q is large, then this sine is of the order of 1. Sorry, I have written the wrong thing. Sorry, please correct. So that's Q. And this is K. This is K. This is Q. And this is K. So, let me again why it is so. This is theta. So this is the change of momenta, which is Q. And this change of momenta, Q, is K multiplied by sine theta by T. And so sine theta is Q over K. Scattering angle is proportional to transfer momentum. If transfer momentum is very small, then you have small scattering angle. So for small q, you have small angle. The presence of large q means that scattering angle is big. So that corresponds to large. So, which means that what has been observed scattering of large angles. This is precisely the situation Rutherford had. So what is the consequence? What is conclusion? The conclusion of this consideration is that the electric charge of proton is not distributed uniformly, but is concentrated on small substructures of the proton. And from already initial experiments, it was clear that the size of this object, small object, should be smaller than 10 to the minus 14. So at least they should be 1 order of magnitude smaller than the size of the nucleon. And then with scattering with higher and higher energies, this bound became stronger and stronger. And so now we remember we discussed this, what is the present day is 10 to the minus 18 centimeters, the size of the port. So that's bottom line. The conclusion is that electric charge is not distributed in all the volume of proton, but it is concentrated on some small object, which means that nucleons, protons and neutrons, are composite systems. Of point-like objects which carry electric charge. And we call these objects partons. Questions? That's the size nucleon, and the size of this object is smaller than 10 to the minus 14. This is 10 to the minus 13 centimeters, and this should be smaller than 10 to the minus 14. That comes already from the first experiments with energies or of the order of few GeVs, 1 GeV, 2 GeVs. But then with the increase of energy, the bound on structure of these partons becomes stronger and stronger. Clear?
I have a question.
Yep.
So these partons are like quarks or?
Well, this is next question which we'll discuss to kind of identify what are these partons. Saying in advance, these are not only in general quarks, but also gluons, because also gluons are inside the atoms. But then it was checked that, yes, at least in scattering of electrons do not scatter on gluons. Yes, objects which are inside and carry electric charge are quarks. So existence of deep inelastic scattering has been uncovered, and this deep inelastic scattering actually dominates when you have scattering of high energy particles. So we came to the conclusion that there are some constituents of nucleons.
Just clarification. How did we distinguish there were point-like particles instead of the distribution of some other way?
So that's what I'm saying. From these first experiments, we cannot say this point like that. It's not point particle, but it's point-like. It looks like point, right? So again, in the first experiments, it was established that it should be smaller than 10 to the minus 14, 10 to the minus 15. But nowadays we have a much stronger bound structure, 10 to the minus 18 from LHC. Because the higher energies you use for collisions, the bigger Q squared. So what is important parameter is Q squared, because eventually you are probing your structure by photons in these experiments. Right? So you need to have big Q squared. You need to have small wavelengths of photon, this virtual photon which hits your system. Okay, another crucial thing to understand how the proton is constructed, or nucleon was constructed, was discovery of Bjorken scaling. Who knows what is Bjorken scaling? Who heard about this at least? Okay, so let me again remind. So we deal with collisions of electrons and protons. Let's take for definiteness electrons and protons. Let us consider this problem in the reference frame, not the rest frame of proton, but the frame where you have some momentum, non-zero momentum of nucleon, so proton, neutron. So let me put N here. So that you deal with collision of moving electron and moving proton. And at higher energies, the energy of proton can be also very big, so bigger than GeVs. And so this is the regime which we are discussing. Right. So let me put here. So we are using reference frame. Where proton or nucleon is moving. And the energy is bigger or much bigger than 1 GeV. The cross section can be written in general, let me put differential cross section, d sigma over dq squared. So which means this is cross section with some value of transfer momentum. It can be written as d sigma 0 over dq squared, and this is scattering on point-like object. That would be if proton is just point-like, has no structure. Multiply by some function, which is function of q squared and Pn. So again, we are in this frame. In fact, we can get the results in any frame, but this frame is very convenient to see physics of processes. This function, which is called structure function, that describes deviation from point-like. So it precisely describes the effect of existence of structure inside the nucleon. So this is what we call structure function or form factor. What has been discovered, and then Björk explained this, that actually this function is not separately the function of q squared and this Pn, but it is function of combination of these parameters x, b, and xb equals minus q squared over 2 q multiplied by Pn. So what has been established experimentally, the structure function depends on such a combination of parameters. So which means, why it is scaling, and this was called scaling. If you increase q by some amount and increase Pn by the same amount, then x doesn't change. Okay? So if you write q equals a times q and p equals p times a, then a will cancel, because you have Q squared here, Q here, and Pm in the first part. Clear? So you can rescale Q and Pm, and X doesn't change. And therefore your structure function doesn't change. So which means the structure looks the same for different energies. You can actually go from low energies to higher and higher energies of proton, energies of collision. And you will have the same in this unit structure function. Ask questions. This is important. I can repeat again. So if you do the following transformation, Q go to A, Q, and P, and go to A, P, and insert it here, then A just cancels and X P doesn't change. And you can say, so what? Okay, might happen. So you will see how important is this scaling and what it leads to. By the way, if you go to reference frame when proton is at rest, so if you go to reference frame where P n is 0, momentum of proton is 0, so which means that for momentum is the mass of nucleon 0, then xb becomes minus q squared, 2 masses of nucleon. And unfortunately, this is the same what people are using in literature as we are using for neutrino, nu, and nu is the energy transfer. This is the energy of initial electron minus energy of final electron. This is energy which is transferred from electron system to nucleon system, to hadron system. So, you know, Bjorken, well, actually people are wondering why he still didn't got Nobel Prize, because that's what he did is really of fundamental importance. So, scaling. Now, how to explain this? And now we will consider how this is explained. You can explain scaling making several assumptions. Actually, Feynman also contributed to this. Sometimes people are calling this Bjorken-Feynman scaling. Let me see what I mean. Maybe I should just use this part. First, that's very important. And actually, that was in 60s. That has this science has been developed. The first, so let me say, scaling first, can be explained under the following assumptions. First, that partons are free non-interacting particles. And you can wonder, how come? So why we cannot see them, these partons, right? if they are free, why they are not, evaporating from nuclei. So very non-trivial, right? So you need to assume this to explain scaling. So which means that this is very non-trivial stuff is behind this observation. This means that nucleon can be considered as just flux of non-interacting partons. Let me put three partons. Well, actually, this is also important, especially for LHC, and then we collide protons, proton and proton. But in reality, we are colliding fluxes of quarks, of partons. So that actually what proton itself doesn't play much role. So at this very high energy collisions, it's just again a flux of partons. This is how we describe collisions of protons. See, you can actually stop me if you are thinking that I'm cheating. So, this means that momenta of partons, and I call this PQ, should be somehow proportional to the momenta of nucleon. This is momentum of nucleon. And this is momentum of parton. And in the first approximation, we can neglect motion, say, orthogonal to the direction of propagation of proton. So it's parallel. Fluxes which are moving parallel in the same direction as protons moving in the first approximation. So let me again write it. This is P. Nucleon, proton, and here are individual partons. PQ. To describe this, we are introducing variable x, which is ratio of PQ over Pn. And this is momentum of individual parton. So x is the fraction of momentum of nucleon which a given parton here. So we have many partons, and total momentum of nucleon is shared by these many partons. So individual parton brings only a fraction of total momentum. Okay. Next assumption. Actually, this is maybe not even an assumption, but something which follows from high energy. So, second, we are saying that scattering on individual partons proceeds independently on other partons. or as we are saying, incoherently. So which means that if we have, again, this picture with partons, and we have electron, which scatters on a given parton, so we have here Q parton, this is electron go in this direction, and I think it's focused on something like this, and then Q prime go in this direction. And others continue as they did before. So what happens, that electron actually hits one of the partons and scatters on a given parton. And others are just like the spectators. Okay? And then you need to sum up interactions of a given electron with all partons. In fact, this incoherence can be just a consequence of the fact that the wavelengths of electron 1 over Q is much smaller than the distance between partons. Again, you see the same story with coherence, how it is realized and such things. So if effective distance between partons is big enough, then it's trivial, right? Of course, then you will have interaction of electron. And if it has small wavelengths, which means that it just probe some small area of the space, then like in atoms, we have, remember, incoherent scattering on different electrons. In the same way here, we have incoherent scattering on different partons inside the nucleon. And so what we should do, we should consider individual scatterings and then sum up. And therefore, d sigma on nucleon over dq squared equals sum of the scatterings d sigma I over dq squared, sum over partons. Like remember, we discussed also scattering on electrons inside the atom, incoherent scattering. You can see the scattering on individual electrons in the atom and then sum up over all electrons in a given atom. Here we need to sum up eventually over partons. So I have written here the sum, but we can substitute the sum by integration. Introducing number density of partons with a given x. So what we are introducing, we substitute, let me write, sum by integration. And for this we are introducing number density of partons with a given value x, fraction of momentum of proton it carries. So, and therefore, number of partons in the interval dx is given nx multiplied by dx. So this is number density of partons with a given x. Remember, x is fraction of total momentum of proton, which a given parton is carrying. And so x changes from 0 to 1 in general. Right? And so for each value of x, we can introduce how many particles with a given x exists. You can treat this also as the probability, which is equivalent, as probability to find parton with a given x. Inside the proton. And actually this doesn't depend on momentum of proton, because we are talking about fraction. If it is 1 GeV energy or 10 GeV energy proton, then this is fraction of this 10 GeVs. Say some partons take, say, 10%, some is 1%. But however, there is a probability that this nx always very small is 1, which means that at some moment of time, all the momentum of proton is concentrated on a single parton. If you use this interpretation as probability, but this is probability is going to 0, and we will see the distributions, and they look like this, and so the probability to find, here's nx, to find parton which carries all momentum of proton is essentially 0, that converges to 0. However, there is some small chance that a given parton has a big fraction of total energy. Questions? So once we introduced this number density, we can substitute the summation by integration over dx. Let's multiply by nx, and then d sigma over dq squared, x q squared. Questions?
I have a question.
Yeah.
So the number density that you have mentioned, it doesn't depend on the momentum of the nucleon, of the proton?
No, in the case of scaling, exact scaling, it doesn't. This to explain scaling, so that we will arrive at the scaling. Later we will discuss also violation of the scaling. Then the answer to your question is that it still depends, but in the first approximation it doesn't. Okay.
We also thought that proton or electrons consist of like 2 quarks that for quarks and down quark, for example. But in this picture, I mean, there is like a sea of quarks.
So remember what I said already, that what we referred before was kind of valence quarks. So to say, I will discuss this a little bit later. So you have many quarks and also quark-antiquark pairs. And for instance, in the proton there are 3 valence quarks, which is U, and D. Those are carrying quantum numbers of proton. The rest have 0 quantum numbers. So you have strange quarks also in proton, but strange and anti-strange. Now, Now we will say already the following once we introduce these distributions. That even valence quarks, they have distributions. So you have U, and D in proton. U quarks have certain distribution over X. D quarks also they have their own distribution. I will discuss this in 10 minutes. More questions?
Does this depend on only, for example, you said that there are some of these partons that carry more momentum than the others?
Yeah.
But like it depends on the mass of them?
Sorry, these distributions?
Yeah.
The answer is yes. Again, wait a little bit. So for instance, we have also strange quarks. Even B quark is present in proton. However, amount is very small, negligible. So you still have some probability even to find B quark or B anti-B, because you need to compensate to have correct charges, correct quantum numbers. Okay? So next step. Is what is this d sigma or dq on the partons? So what we are saying that since partons are point-like, then d sigma parton, d sigma q over dq squared equals d sigma q0 over dq squared. And this is cross-section on point-like particles without structure. So let me put here Q. So the picture is like this. We can see the scattering of electrons on point-like partons. Partons have no substructure, so it's just like a scattering on point-like object. And then we need to sum up or integrate interactions over all the partons in the nucleon. Not all, those who are interacting. So gluons are also kind of partons, but they have zero charge, and therefore we shouldn't include this in our integration. And of course we need to take into account the electric charges of partons. So let us consider now the scattering of electrons on individual partons. So this is what is producing here the sigma 0 over this one. We have now partons. Gamma. And it's parton in the beginning with momentum PQ and the final is P prime Q. And photon has 4 momentum Q, which is transfer momentum as we had written already. So let us write energy momentum conservation for this part, and we can write it as PQ plus Q equals PQ prime. Or you can write the same momentum including electrons explicitly, because Q is P electron minus P electron prime. This is energy momentum conservation for this process. So you can consider also this part. So you have collision of parton with momentum PQ, with photon with momentum Q, and in final state you have another parton with momentum P prime Q. Right? So let us square this expression, and what we will get is mq squared plus 2pq plus q squared and this equals mq squared. So I square this expression. Pq squared gives you the mass, right? The particle. Now this is cross term, this is q squared, and on the right hand side I have again the mass of particle. That cancels. And what I'm getting is the following. I'm getting that 2pq equals minus q squared. Let me write pq. Remember, we have written this as x multiplied by pn. And insert in this expression. And so what I will get is 2x pn q equals minus q squared. From here I'm writing that x equals minus q squared to pnq. And we realize that it is coinciding with Bjork invariant. Now I have deleted already this expression, but let me repeat it. Now d sigma nucleon over dq squared equals d sigma 0 over dq squared multiplied on n xb. This is xb. So that's what we have written before we identified x and xb, just on the basis of scattering on individual partons which are point-like. What we have shown that x, the fraction of momentum which is a given parton is carrying, coincide with Bjork invariant. And this is nothing but scaling, right? So because this is structure function, and it depends only on this combination, xb. And so in this way, we have derived scaling. That's scaling. We derived essentially the structure function, because this is on point-like object, is the function of xb. By price, assuming that protons are the fluxes of non-interacting partons, the partons are point-like objects, right, and not interacting. So that's our assumptions. So which means that the scaling implies are fluxes of non-interacting among themselves. Point-like objects. Also non-interacting, which is free moving point-like objects. So remember, we introduced Bjorken variable. Now we can say what is the physical meaning of this Bjorken variable. Bjorken variable gives us fraction of total momentum which a parton carries, parton of which scattering occurred, fraction of total momentum of nucleon. Let me edit it. Gives fraction of total momentum, actually gives the for momentum of parton on which scattering occurred. Okay? So xb gives fraction of momentum of nucleon, x this way. This fraction gives for momentum of parton on which scattering occurs. I will repeat now. For momentum is given by PQ equals x Pn in this way. So, if scattering occurred with a given q squared on Pn, and we have this value of the Bjorken variable, then this value gives us momentum of parton on which scattering occurred. So knowing this tells us what was the momentum of parton on which a given scattering occurred. So if we know this, because this we measure, right? So we know what is q squared, we know what is Pn, and suppose we have a given event. Because in different events you have different q squared, right? But suppose we have some event in which a given q is realized. Then we can say what was the momentum of parton on which this scattering occurred. So x, introduced in this way, has certain interpretation at the level of partons. questions? Okay, so let me add what is really a structure of nucleons, which we know now. Maybe I just write once again this type of the picture. So we have XB, which is Q squared 2 Q Pn. And this is measured in each of event, right? So this is at the level of hadrons and electrons. So we know what is Q, we know what is Pn, and we can construct this XB. That gives us X equals XB, and this is fraction of momentum of nucleon. So X equals Q or Pn. And this is the pattern on which a given scattering occurs. Now, as I said, Nx is the number density of partons, the function of x, and what we usually show is x multiplied by Nx, and this has a dependence of this type. Maybe I should write this a little bit better. Has a dependence of such a type. So Nx itself is a divergent union. So you have many very soft partons. This picture actually is the contribution of two things. One is valence quarks, and those are quark-antiquark pairs. This is quark-antiquark pairs. And this is the distribution of valence quarks. And valence quarks are quarks which take, which bring the quantum numbers of proton. So in the case of proton, those are U, and B. Valence quarks have a distribution of this type, but on the top of this, there are also quark-antiquark pairs, and since they are quark-antiquark, then the total quantum number is 0, but they bring momentum, and so the sum of these two gives you such a more complicated distribution. In fact, these quark-antiquark pairs can be produced by usual quarks. So suppose you have 3 valence quarks, and then those emit gluons and then produce quark-antiquark pair. So bottom line is the following. What are these partons? So they are valence quarks. Quark and quark pair. And something more, which actually mediates strong interactions. And those are gluons. And we will discuss gluons next. So, which means that really nucleohydrons have complicated structure, and there are distributions different, by the way, of U and D quarks, and also there are distributions of quark-antiquark pairs, and different quark-antiquark pairs have different distributions. So, for instance, you have also presence of, say, charm quark or charm bar, and their distribution is very strongly suppressed, so that if this is quark-antiquark of usual type, U bar, D bar, then strange quarks, they have smaller, charm has even smaller, and B is even smaller number densities. So questions? That's it for today.
So quarks are only free inside the nucleons.
Yes, so we will discuss this. This is what is called asymptotic freedom. Let's see, there are some questions here. They have yet proven that the partons are quarks, right? So they have these partons, they have this structure. But then what was done, different scattering processes have been considered. It's electron, muon scattering, neutrino scattering, then even hadron scattering. And so you introduce some quantum numbers. Of course, you need to introduce some charges for these partons. And eventually it was established that everything is consistent, that you have partons and quarks. Okay? Questions here? No? Then we will continue tomorrow with gluons and strong interactions. Okay, so I want to chat with you, right? So we discussed, and I will talk with everyone. I'm today with you, and actually you are the next in this list of students, right? So again, you can come like today or say, after lecture to my office, so that we will discuss. I'm doing this individually as well. So we can discuss here, just they will leave and then we will discuss. So easy.
I have a question here.
Oh.
Ila.
Yeah?
So when we see on the graph the X dependence and the number density, so the quark and antiquark is so it just decreases from U to charm quark. So what is the reason behind? Is that because of the mass?
Right, exactly, yeah. Because of the mass. Because these quark-antiquark pairs are produced in this way. It's through gluons. And then you need to produce more and more massive quarks, and then the probability for this is small. It decreases with mass of the quark.
Thank you.
Okay.
Also, since these are the particles, the quarks are particles, we said that the responsible of the mass of the total nucleon are mostly of the mass of the quarks and the energy of...
Yeah, for light, for proton, a neutron for those, which are mostly composed of light quarks, so U and D.
But if we are considering that they don't interact between each other, like how the mass of the proton.
Oh, so we will come to this. And saying in advance is that this structure which we see is at high energies. When you probe proton by good microscope, right? So how they are, sitting and how they are confined, as they are saying in the proton. This is physics of low energies. So this confinement and because of strong interaction forces become strong at low energies. This is just next what we will discuss. And at high energies, the forces become weaker and weaker. So which means, actually this is also important, the general principle is that things which you are studying depends on the resolution of your microscope. Because if you have bad resolution, you see just something. You see one person is going, then you have better, resolution. You see that the guy is bringing some kit with him. So that's very general. It's everywhere. So things how systems look like depend on the resolution with which you are looking at this. And the same is here. So the proton looks differently at higher energies, of good resolution microscope and bad resolution. Sure. Okay. So why not to sit down here? I will bring you a mask, just to obey all the rules. So let me ask you a few questions. So you had, you studied in which place before coming to
in Palestine.
Oh.
I did the master's degree in Palestine, but my project was at CERN.
So what was at CERN? What is your project?
At Alpha experiment.
Which?
Alpha experiment. It's more electronics and radiation resistance
so
of electronics.
you were experimentalist?
Yeah. But I did the diploma because my background is the theoretical part is not so good, so I was right for
But in Palestine, in which city, which place?
Gaza.
I see. Interesting. I think we had some, before we had a number of students from Palestine, but from the various places.
Yeah, I know all of them.
Oh,
Yeah.
okay. So tell me, which courses you had? Of course, you filled in some forms when you applied, but I was not on selection committee. So you studied particle physics or something?
No.
Nuclear physics?
Yeah.
Nuclear physics.
But this was in the bachelor degree.
Okay. So it was 4 years or what? How many?
It's 4 years, yeah.
4 years.
But actually it's 3 years because we have dedicated courses in our country. It's related to history and other things. So the physics courses was actually 3 years.
And at CERN, you visited CERN? How it worked?
Yeah, I was a technical student for 8 months. Actually, I did 2 jobs. The first one was about an experiment in alpha, and the other one was trigger efficiency analysis. And during that time, I was at the European Scientific Institute, ECPAP, in Akshat. I did 2 courses.
So you had no courses on quantum field theory?
No.
No. But quantum mechanics, right?
Yeah.
So, in future, what are you going to do? What do you have some plans? You want to be a theoretician eventually, or what? Or
No, actually, experimental physics.
you want to do experimental physics?
Yeah.
And you want to do PhD where? To go to CERN or to what are your plans? To Switzerland, because CERN is not giving PhD degrees.
Yeah, and there is PhD positions for Palestinians in Zurich.
Zurich?
Yeah.
I see.
And they give the fund, but the problem is, I applied before, but they said the course is not enough because I don't have particle physics course or other things. So the problem is the theoretical background. We have only quantum mechanics and mathematical physics, but we didn't even get to the tensors or other complicated things. So that's why.
And Zurich is this ETH, or what is this place?
Yeah.
It's precisely where this Darius Parugi, who was my diploma student, and he's now postdoc working on this big physics. So tell me, is my course, do you understand what?
Yeah, actually, until now this is the most course I enjoy because it's more related to physics and I can understand everything physically. The other courses are like more abstract.
Well, but you need to understand that I'm trying kind of knowing what is the level of students and not assuming that you know field theory, etc. I'm just eventually when you want to compute cross sections, you need to know, especially if you have these loop diagrams and all the things. So this is necessary. You need all the yes. I'm close to experimental physics. But to work on professionally, one is supposed to know.
Yeah, actually, I did understand all of the courses, but this is like the most understandable one.
Well, actually, we had a number of students which made experimental careers. We had a student, that was a long time ago.
For Mustang. For Mustang? He worked at CERN. Actually.
Yeah, no. That's different. So it's a girl. I think she was from maybe Venezuela, or she became a spokesman of NOVA collaborations, of the job. So spokesman of huge collaboration with several hundreds of people. I think there's some other also people also quasi document researchers, etc. So it's I looked at your solutions of the exercises, and actually several are not solved correctly. So you will check this on Tuesday. Knowing your background, don't hesitate to ask questions.
Some of them, or?
Not all. I don't remember exactly, but we will check and then I will return to you. these exercises with marks. So what I'm saying, don't hesitate to come and to clarify it, so, because it's important not just to lose the time. I'll be happy to explain in more details. So another question, should I move slower or this kind of a speed which I'm talking and writing is okay?
That's okay.
So you have time to...
Yeah. We have time to write them.
So eventually you want to apply to Switzerland eventually, right? To these courses.
This is what I have in my mind right now, but it's okay if I can apply any place, other places in Switzerland.
It depends on you what you want
Yeah.
to do. Okay, so thank you, and keep in mind that come to me and you can send a mail that you want to discuss something.
And both of the homeworks are like...
Sorry?
both of the homeworks,
No, I checked just one. I will check probably today, tomorrow, the second one, and then we will discuss both exercises on Wednesday.
Okay.
Okay.
Thank you.
Yeah, sure.
Bye.
Bye.